Hello, we're back again with Landau Lifshitz chapter 1, and now we're doing question number 4. Question 4 is another calculating the Lagrangian for a specific system, and in this case we've got a weird setup in which these two masses are set to pivot around the top of this rod and are attached to another set of weights at the bottom. Now this diamond shape can be stretched out or pushed in, which would result in the bottom mass, M2, rising or falling. So we define the stated system by theta, the lengths of the segments A, and what's interesting about this is that the system is set to rotate at a constant angular velocity called omega. And that's what drives the smaller masses to pull outwards. So we're going to start by defining our coordinates. This time x will be pointing outwards, y will be pointing upwards, and we need a third coordinate, z, because this motion is three-dimensional. So for each of the mass 1s, the kinetic energy is 1/2 m1 times x dot squared plus y dot squared plus z dot squared. Which I'm going to immediately transform into the theta coordinate. For mass 2, it's a little bit simpler because mass 2 can only move up and down, which means its kinetic energy is determined only by y dot squared. And again, immediately converting to our theta coordinates. So the total kinetic energy is just going to be 2 of the kinetic energy from mass 1 because there's 2 of them, and 1 of the kinetic energy from mass 2. The potential energy will be similarly straightforward because all we have to take into account is the vertical distance for each of the particles. Now that we have the kinetic energy and the potential energy, we can combine them all together to get our Lagrangian. And then we'll be done. And next up, I think we have something that's a little bit different. We won't just be calculating the Lagrangian.